This meeting is being recorded.
So back to class. Today is output devices, and we're going to introduce power electronics and then use it to display on displays and move motors. And then we're beginning very important sequence once again. Monday recitation with a dream team of star machine builders to introduce machine building. Class next week will be on machine building. And then over the next 2 weeks, you're going to make machines, all towards the goal of come to a lab, not to use a machine, but to make a machine, and rapid prototyping of rapid prototyping. And so to do that, initially in the early schedule, this was molding and casting, but we flipped the order to move up output devices to be able to cover motors. So the assignment is add an output to a board you've designed and make it do something. And the group is to understand the power consumption, which I'll talk about. And we're going to cover all sorts of different outputs, but in particular displays and motors. This is a link to electrical safety. And this week is a bit like machining week in that as we go up in voltage and in current, this becomes more hazardous. So a milliamp is harmless. Inside your muscles, 10 milliamps contracts your muscles and you can't control them. And 100 milliamps inside your body is enough to give you a heart attack. Now, inside your body is a mega ohm, but inside you're only kilo ohms. And so anything that can actually puncture your skin and connect internally means low voltages can be very dangerous. At a gradient of a kilovolt per millimeter, you break through dielectrics and it'll go through insulation. So some of the things to worry about is capacitors in power supplies can stay charged for a long time and give you a shock even if there isn't power. Coils, if you have a current going through them, when you turn the current off, the magnetic field goes back into a voltage and can give you a high voltage spike. These can hurt you, they can hurt the electronics. If you connect power with the wrong orientation, you can fry the electronics. And there's a whole subsection of, these are all different versions of components that protect circuits from getting fried and protect circuits from frying you. And so what this means is as you go up to higher voltage and higher current, you should approach this just like machining. Don't do it in the middle of the night. Don't do it alone. Don't do it when you're tired. Don't do it with a messy workspace. Make sure you understand how to turn things on and how to turn things off carefully. All those same sort of concerns apply. So the goal of this week is not using lots of batteries. So we're going to need to power, oh, actually, let me jump to first show you. Ling Dong did a star featured assignment. I'll come back and show more on this, but he did a great example of lighting displays. He made crazy big boards just for the fun of crazy big boards. He moved motors. He made loudspeakers make sounds. He did one of just about everything this week. So we need to power it. Increasingly, our favorite power supply is USB. This is a page on specs. USB 3, any USB 3 port can give you 0.9 amps at 5 volts. And remember, I times V is power. So that's about 5 watts. And that's enough current to move a motor, not on a big shopbot type machine, but on, for example, the desktop milling machines or a laser cutter. You can power it right off a USB 3 port. So little USB chargers just cost a few dollars, and that's a very handy power supply. And we'll see this USB 3 hub. We'll see this in machine building. These sort of USB 3 hubs, this lets you power multiple devices, and it's switched so you can turn them on and off separately. So for things that can work at 5 volts and up to 1 amp, this is our favorite kind of power supply. Now with USB, you can negotiate above that. So if we take the USB solder hot plate, this cute little device, this thing, this is USB powered, but it's 60 watts, not 5 watts. So you can go up to, you can negotiate with USB 3 to much higher voltage and current if the power supply understands it. That's not for standard data ports, but you can use it for heftier USB supplies to get more voltage and current from it. So we'll make lots of use of USB power supplies. This is a vendor of bench supplies. Switching ones are electrically noisy, but low cost and fairly efficient. Linear ones are cleaner power, where you need lower electrical noise, but they get hotter and they're more expensive. And the bench supplies like these ones are very useful because they let you separately control voltage and current. And if you pick voltage, it'll tell you the current you're using, or if you pick voltage, it'll tell you, if you pick current, it'll tell you the voltage. So those are handy things to have at your workbench. Supercapacitors here store less charge than batteries, but they're very easy to both control the charging and discharge. They're limited typically to lower voltage, but these are ways to make local power storage. For batteries, for things like drones, we use lithium polymer batteries. Charging them is much more sensitive. You can kill them, you can make fires, but there are these common commoditized boards that have built-in chargers to control them. And if you're using those, you need to be aware they're also a fire hazard, and you should store them safely for fire hazard. And then finally, there's a lot of research on wireless power transfer, where you can make coils and then you design them so they have a resonance, like pushing a swing, but electrically. And that lets you send non-trivial power over reasonable distances, like a few meters, to power things wirelessly. So these are all options. And of these, USB is so ubiquitous. By far, that's the most common, easy way now to power these devices. Let's see, Michael's asking about dangerous. So the issue with supercapacitors mainly is just they're limited depending on which one you get to, like 1.8 or 3.3 volts. If you go over that, you kill the supercapacitor. I'm not aware of other dangers on supercapacitors. Oh, but yeah, what I was referring to is power supply, not a supercapacitor. So if you look in a power supply, you'll see really big capacitors. These aren't supercapacitors, but these handle much higher voltages with reasonable amounts of charge. And these big power supply capacitors can store substantial charge even when power is off. And so it's very easy to get a shock from them. So remember, power is current times voltage drop, or the square of current times resistance, we're limited by how much, you can be limited by how much power you put in, by the battery lifetime. You can be limited by just dissipation of getting heat back out. So one of the things I want you to do is measure power consumption this week. So one way to do it is if you just have a bench supply, when you turn it on, it'll tell you the current you're drawing. One thing you can do is whatever your circuit is, on the ground side, you put, for example, a 1 ohm resistor, and then you measure the voltage across that going into ground with a sense resistor. Another thing you can do is, if this is your circuit and power is coming in here and going out there, if you clamp a coil around it, and alternating current generates a current in the coil, or just a DC current makes a magnetic field, and you can use a magnetic sensor to pick up that and calibrate it. And so those are all ways you can take a circuit that's running and measure the power consumption. And so the group assignment this week is pick one of your devices and just look at how you actually measure the power that it is using, which again is going to limit things like battery lifetime and heat transfer. Okay, so with that, we're going to start in. So the first example is, this is a red, green, blue LED, and I'm varying the color and the brightness. So this is one package that has 3 lighting emitting diodes in it. And so these can be common anode or common cathode, meaning you have 3 LEDs, and there's a common connection either to their anode or the cathode side, and they're red, green, and blue. And so the circuit here is pretty simple. I've got my processor. This is a tiny 45, so I'm using an ISP. Here I'm bringing in external power. I'm regulating it. And then here's my RGB LED. These are the current limiting resistors. Remember, LEDs turn on so fast that you need to limit the current with them with a resistor. And I've got a smaller resistor on blue because blue LEDs are less efficient. So to get the same brightness, I have a smaller resistor. And then the key thing I'm doing is pulse width modulating. And today is all about that. So if the voltage is on, the LED is on. If the voltage is off, the LED is off. But if you put out pulses, these pulses can run at, say, megahertz. The LED switches in nanoseconds, but your eye runs at about milliseconds. So as long as these pulses are faster than your eye, the brightness of the LED is the average pulse rate. So if you make skinny pulses, it's dim. If you make fat pulses, it's bright. And so by switching the LED between all on and all off, and just by varying the duration, we vary the brightness. And so that's how you control them. And a good way you can test is if an LED is pulse width modulated, if you shake it really quickly, what you'll see is discrete little pulses of light, depending on how fast it's being pulsed. So in this example, what I'm doing here is, we'll talk more about this. The processors we're using have modules in hardware that can pulse width modulate, where you just tell them the rate to modulate, or you can do it in software. So here what I'm doing is I have a loop, and in stages, I'm turning on I pick which pin to turn on, and then I vary the time I'm on versus the time I'm off. And then I'm slowly varying the on versus the off time. And then I'm cycling between the different pins. And so then that takes me through the red, green, but by using those, I can continuously vary the color of the LED and the brightness of it. And this is in fact 1 pixel of what's used in the giant kind of jumbo displays. You do need to be cautious. These RGB LEDs, many of them look the same, but have completely different pinouts. So you need to check the pinout for the one you're using. So that's LEDs. You can get programmable LEDs called neopixels, and I'll talk more about that in networking week. This is a vendor that sells super bright LEDs that can be so bright you can't look at them if you want brighter LEDs. And then you can get what are called electroluminescent wires. You can get panels and wires that it's a different light generation mechanism, but give you distributed light. So that's RGB. Next, I'm going to cover here. These are much, much, much brighter LEDs. So if we take this LED, let's see, I'm looking for if it lists the lumens. But we can just see from the power, this LED can take 20 milliamps. This one here takes 150 milliamps instead of 20 milliamps. So can handle much, much more current. And these little LEDs are so bright, you can't look at them if they're all on. So right now I'm really limiting how bright I turn it on just so I don't oversaturate the camera. But these LEDs are so bright that when they're all on, you can't even look at them. So first, just a little detail. This is an example of the leads are underneath, so you can't solder this with wire. You need to do it with reflow. And the crucial thing now is these LEDs can take, what did I say, 150, 180 milliamps. A processor pin is what we've been using so far. We have the pin, we have our LED, and our current limiting resistor. The pins are, a typical number is 50 milliamps is what the pin can provide. So our pin can't provide enough current. So to light this LED, we need a transistor. So one of the main parts for today is this. And this is a somewhat life-changing part. So this little transistor handles 5 amps and it handles 30 volts. So this is a MOSFET. Let's see. For transistors, there's bipolar transistors we're not going to use. We're going to use MOSFETs. And there's 2 kinds. There's N and P. So an N MOSFET, you draw like this. And you can think about this roughly as a switch. It actually acts like a resistor, and the resistor is a function of the voltage. And so a key parameter for this is RDS. And so RDS here is 42 milliohms. So what that means is there's a gate that controls it. There's a drain that gets connected to the load, and then there's a source. And so for an N MOSFET, the gate gets controlled to the processor. The source goes to ground, and then the drain goes to our load that goes to the power supply. So the N MOSFET is a sink of current. Current goes into it. A P MOSFET, on the other hand, is the opposite. on a P MOSFET, you draw it with a circle there. This goes to the supply. Here's our load that goes to ground. A P MOSFET is a source of current, and N MOSFET is a sink of current. I'm not going to explain why that is. There's a class I teach on device physics where I explain what's going on inside. For now, just take it, one current goes into it, one current goes out of it. So an N MOSFET is a sink of current. And so on this board, I'm doing a few different things. So if we look at the schematic, you'll see I don't have resistors. And the reason why is a diode has a drop, and 1.6 volts is a typical diode drop. And so if I stack diodes up, and if this adds up to my power supply, then I'm not going to pull too much current. So if you stack up diodes, you don't need a separate current limiting resistor. And so in the schematic, what I have here is I have 3 strings of diodes. Each string adds up to my supply, and then I'm powering them in parallel so I can run more than one string. And then all of that goes to my transistor. Now, in the transistor, you'll see I do have a resistor here. The reason that's there is we have our processor going to our transistor connected to our load. When I turn on the processor, initially this pin is an input, not an output. And so the voltage isn't specified here. And so the transistor could be doing anything. And so a common thing is to have a pull down resistor here. And what that's doing is until you program the pin, it's keeping the transistor turned off. Then when the processor turns on, it can easily put a voltage over that resistor. So that's just a resistor to keep the transistor off until I need it. Once I do that, then the code is very similar. All I'm doing here is pulse width modulating, but now I'm pulse width modulating with much, much brighter diodes. Just 2 things to be aware of. Remember, power is current times voltage. That product, meaning in this case, the voltage is the drop across the diode. That can be so much that these diodes get hot. And in fact, they can get so hot, there can be a thermal runaway, where as they get hotter, they conduct more and it diverges until it fries. So you need to be aware of the temperature of them in the thermal load. And once again, these can get so bright, they can actually hurt your eyes, is something to be aware of. Okay, so that introduces power transistors. This next example is an array of LEDs. And here I'm using a famous trick. This is a data sheet on the trick from an engineer named Charlie. So this is called Charlie plexing. The obvious thing is if I have N LEDs, I take N pins and each pin gets an LED. So that would need lots of pins. But if you look at this video, I don't have nearly as many pins as I have LEDs. So the Charlie plexing trick is the following. I'm going to make an array of LEDs. And I'm drawing this in a grid. They don't have to be in a square grid. They can be in a line. They can be in any shape. Let's make this 3 by 3. Okay, here's my processor. So normally I'd need a wire going to each one, but here, what I'm going to do is I'm going to take this pin and I'm going to take it to all of the cathodes. Then I'm going to do something crazy and I'm going to take the same pin and I'm going to connect it to anodes. And finally, I'm going to remove the ones on the diagonal because those don't work. And so here's what's going on. Each pin can be low, high, or it can be an input rather than an output. And so, for example, if I make this pin a 1, if I make this pin a 0 and this pin an input, the 1 here goes to, I've got 1 here, and then if I look here, I've got 0 here, and so that doesn't turn on. But what? So that diode doesn't turn on. But in the opposite direction, I've got a 0 here, and then through here I've got a 1 here, and so this diode is off. This diode turns on and light comes out, and meanwhile none of the other diodes turn on. And so if you have 1 pin at 0, 1 pin high, and all the other pins tri-stated, one diode is connected backwards and doesn't turn on. The other diode is connected forward and it turns on. And so what that means is if I've got n pins on my processor, I can control n times n minus 1 LEDs. The -1 is because the diagonal doesn't work. So this is a link to a data sheet that explains that. Oh, it looks like that link is broken. So I'll fix the Charlie Plex link. But Charlie Plexing lets you control n times n minus 1. And so there's a question, Dorian. There are all sorts of use cases for this where you can use this and you can have diodes, then you can have lights or sensors or switches to make n things going to n squared things. In this case, I've got my pins, and each pin is going to rows and columns, and then I've got the current limiting resistor. And so you can use this to make square arrays. You can also use this to make linear arrays, but you can control the square of the number of pins. So that's Charlie Plexing. Next come displays. So this is a liquid crystal display. And so I'm putting text out on it. That used to be what we used. Those are borderline obsolete now because of these things. This is an organic LED display, OLED. And this is a bitmap display that lets you talk to the pixels directly. See, Adrian has a link in the chat of driving an OLED. So these OLEDs cost just a few dollars each and give you a bitmap display. They speak the I2C protocol that will talk about that. Mikhail, I'll talk about bigger screens shortly. So with these OLEDs, it's a fairly non-trivial protocol. There's a standard chip to talk to them. There's a number of libraries to talk to them. And in this example, I'm doing this with a really simple processor, a Tiny 45. And so I did this one from scratch. So this is the code to talk to I2C. And I'll talk about that in networking week. This big block of text is the character generator. To start, all the LED OLED knows how to do is turn on pixels. So this is where I define the characters. This then handles the communication. And once all of that's done, you just send messages to it. So that's doing it from scratch. Usually you won't do that. There are multiple libraries that make it easy to talk to those. And so with that, you can put arbitrary text on the screen, and not just text, you can address it graphically. And so if we go back to Ling Dong, he went crazy with this assignment. He made a menu, and he did 3D graphics. So he's rotating those. If we go back to his menu system, this was a teapot that he's rendering on it and rotating. You can go through the video. He did diffusion limited aggregation. He drew fractals. He did all kinds of drawing on the OLED. Now you can buy these OLED comes in a range of sizes. There's a non-trivial kind of competition between OLEDs and TFTs. So if you look at OLED module, you can get OLEDs, jumbo TVs, one of the ways they're made is OLEDs. So you can get the OLED modules in a range of sizes. Then thin film transistors modulate light rather than generating light. Historically, the TFT modules were bigger than the OLEDs, but that's continuously evolving. But in general, the TFT modules, you can get bigger ones than the OLEDs at somewhat more costs, still very easy to talk to. So with a TFT module, then again, there's standard chips used in them, and then this is a library to talk to them. So here I'm using a D21 because I need more space. I don't need the pins. I need a processor with more memory to store the code, and you can use a SHAO for that. And then this is using a communication protocol that will cover in networking week, an SPI protocol. And then once you do that, here, I'm not using my code, I'm just using demonstration code from the library. But this is the library's demo code running through a sequence of things on the TFT display. So common ones for these are a few inches big. Again, it's a bitmap display, so you can do arbitrary graphics on it. And once you have this, you can do all kinds of debugging and communication from your projects to have these kinds of screens. So we'll talk more about the protocols they're using to communicate in networking week, but I2C or SPI are most common for that. So that's LCDs and TFTs. And then electronic ink came out of my the lab I run at MIT. A colleague, Joe Jacobson, invented it, and you can get modules for e-ink. They're not, the cost is actually beginning to come down. And what's nice about these modules is they're non-volatile. So once you turn on the display, you can take away the power and it keeps displaying the same thing. Jason is making a note that running the TFTs at low power. So it's not zero power, but it can be lifetime battery. So the cost of these have been coming down to make e-ink displays for when you want it to be non-volatile. And they also have very good contrast in bright light. Okay, next, This next one makes me sad because you'll never do this. This is a simple component. All I have is a few resistors, and this is making a video pattern. And from there, you can do all sorts. Let's see, this is a, this is in software. Let's see, let's get through the ad. This is generating video signals in software. And this is for analog displays that nobody uses anymore. So this is generating color graphics just from an embedded processor. The processors we're using are fast enough to generate video waveforms. Unfortunately, screens that take analog video are no longer common. And the digital video standards like HDMI are complex enough that you can't easily synthesize them in software. We use them on boards that know how to support them directly. Jason is noting CRTs in retro gaming. If you have access to old cathode ray tubes, then these links are how the processors we're using are fast enough that they can actually generate the analog waveforms. Okay, next is we're going to make audio. So here is a board with a D11. I've got a power transistor connected to a speaker, and it's making beeps. So I'm varying the volume and the frequency. And so this is what's going on. To vary the frequency, this is high frequency, this is low frequency. And to vary the volume, I'm varying the on time versus the off time. So I'm putting out pulses to the speaker, and it's slightly confusing in that audio, my voice has a shape, the waveform. And when we're crossing zero, there's no signal. When it's loudest, the signal is strong. And in between, I'm varying the pulse rate. So to vary the frequency, that's this time. To vary the volume, it's the on time versus the off time. And I've got a high frequency that I'm using to generate the pulses. And the reason we do that is if we go back to our transistor, there's a key curve. Okay, so this curve is the voltage versus the current. And the different lines here are the gate voltage. And you see, once we get up to a gate voltage of a few volts, these all overlap. The slope of this curve is the resistance. And because power is I squared R, we want the resistance to be low. So if you use the transistor, we could vary the current by varying the voltage and varying the resistance, but we would be dissipating power. Instead, what we do is we make the transistor all the way off or all the way on, and we vary the fraction. So if we come back to my beeping speakers, in this version, what I'm doing is in software, this is just like the LED. In software, I'm turning the pin on and off, and I'm varying the frequency. Then in this version, what I'm doing instead is for the processor, all of the processors we're using have a special module for this. So this one I was doing with the D11C. And so if we go to the timer counter modules, what they can do is, let's get to the right part. Here, you set the counter counting, and then you put a number in a register. And when the count crosses that number, the pin goes high. When the count goes below it, it goes low. So rather than you switching the pin on and off, you just set how fast it counts, and you give it a number to compare to. So in this version of the code, what I'm doing is I'm varying the comparison number in the register, and then the processor is doing the generation of it. And so that's pulse width modulating to make audio for a speaker. Now, you can go well beyond that. This was a student who did a more complex code example. And what that one does is this. Okay, so all of that music is being played by the processor, and what it's doing is wavetable synthesis, where it's storing a waveform, and then it's playing it out through pulse width modulation. And then a few other notes. What I'm doing is crude in my little beeping one. It looks like this. I've got my processor, I've got my N MOSFET going to ground, and then I've got my speaker that it's driven by a coil, and then there's the cone. And here, what I'm doing is when I pull current here, it pulls the speaker in. When I turn the current off, the speaker just mechanically comes back. So in fact, the speaker isn't centered. I've got it off center. And so it's not driving the speaker optimally, but it's a simple way to do it, and it's good for a beep. Better than that would be, you'd like to drive the speaker with current going in both directions. And to do that, you need to use a part we're going to talk about called an H-bridge. And what's called a Class D amplifier is essentially driving a speaker with an H-bridge, which again, I'll talk about in just a minute. And then finally, for audio, you can get chips that implement full synthesizers. So General MIDI is a standard set of MIDI libraries, and you can get these really interesting chips that synthesize not just beeps, but musical instruments, and can interpret, for example, MIDI audio files, so dedicated audio chips. Okay, that's driving a speaker. Once you know how to drive a speaker, this is a fun video I like. This is somebody explaining, here, I'll mute. He's explaining what I just covered about transistors and coils, but then he uses all of it to do this. Let's get up to, so he's got power transistors pulling current through coils, making solenoids that pull on magnets to make linear actuators. Okay, now we're going to do DC motors. So this example is spinning a motor, and I'm spinning it fast and slow, forward and backwards. And I'm using this beloved part. So what's going on in this part cost $1 in quantity. And there's a lot going on here. It's an H bridge. So here's a coil. That's our load from a motor or a speaker. So I've got two N MOSFETs on the downside. I've got two P MOSFETs on the high side. So if I turn on this one and this one, current will go that way. If I turn on this one and this one, current will go that way. And if I turn on this one and this one, I pull both sides down and I stop it. So that lets the motor or the speaker go in one direction or the other, because I can move it in either direction. This is called an H bridge because the circuit has the shape of an H. Now, what's going on in this package is that's the H bridge. That's the 4 transistors. And they're quite hefty. In this part, it can go up to 3.5 amps and 44 volts. But one thing going on here is the charge pump. For the MOSFET, it depends on the transistor, but we're using what are called logic level MOSFETs that turn on at a few volts, so say 5 volts. That goes from off to on. Here, though, the high side might be, say, 24 volts is how we're powering the motor. So on the high side, it goes between 24 volts and 19 volts to go from off to on. But our processor that's running our 3 or 5 volts can't make that high voltage. So the charge pump is a neat circuit that lets you put in a low voltage and it makes a high voltage. So we need the charge pump to control the high side of the circuit. Then this has a comparator. Because we want to pulse width modulate, you can pulse width modulate in software, or you can put a load resistor here and the chip itself knows how to pulse width modulate. And then finally, in addition, it knows how to detect overcurrent or over temperature. And rather than killing itself, it'll turn off if you overdrive it. And so with that wonderful part, here's my processor. Here's my H bridge. You'll notice I'm using fatter lines, PCB trace with calculator. You can look up tables or formulas to calculate trace width. Power is I squared R. There's some resistance in the traces. Once you start pulling more current, you care about this. If you use a skinny trace, it actually will get hot. The dissipation in the trace becomes noticeable. So when you start pulling more current, you typically use fatter traces. Then the other thing is this capacitor. So this processor runs at 3 volts. USB is giving me 5 volts. This capacitor is for the regulator, 1 microfarad. But you'll see I have a 0.1 and a 10 right next to it. When this switches, when the H bridge switches, there's a glitch in the power supply. And so the smaller capacitor acts like a filter to try to filter the glitch. And the bigger capacitor gives me a little bit of extra local power storage until more current comes in from the supply. And so I'm adding extra bypass capacitors around this. If you don't do that, you can get really subtle bugs where, like, when this switches, it actually makes the processor itself reset. Okay, so then with that in, here is my code And then just in this case, I'm doing software pulse width modulation, and that lets me spin the motor. And Adrian has an example of doing that with Xiao's. Okay, so that's DC motors. Then these motors have a curve of, if you look at, this is how fast they're spinning. And this is, call it the efficiency, the percent of power coming out through the motor. And they're very inefficient at low and high RPM. And there's a place in between where they're happy. And this might be, say, 10,000 RPM. So if you want to drive something with torque at low RPM, you can't just drive the motor slowly. What you do is you add gearing. And so you can get a gear head DC motor. It is a DC motor that has gearing built into it. So the motor can spin fast, but you can drive the load more slowly. And then you can get these cute little motors that are DC motors, but they have a rotor that's unbalanced. And so when you spin them, it vibrates. And that's how you, for example, feel your phone vibrating. And then you need to be aware the RDS is fairly low, but again, when you're putting a lot of current through them, these the motor control circuits can get fairly hot. And so, if it just gets hot to the touch, a common thing is to add a heat sink to improve the airflow out of it, to improve the heat transfer. Let's see, Hank is adding, this is progress on the VFD. Nice. And yeah, I'll talk about that shortly. Okay, so that's DC motors. Servo motors. So this is a special kind of motor. Oh, and in fact, actually, I'll show you. Let me add a link to this. So in my lab, we recently got a new X-ray microscope. And this was a video I did of a servo motor. So here's the DC motor. Here's a reduction gear train. And then here's a potentiometer measuring the angle. And then here's a little control circuit. So it's very simple to drive these. There's almost nothing going on here. All you do is provide ground power, and this is a pulse width modulation signal. And universally, these use 50 hertz is the frequency, and between 1 and 2 milliseconds is the angle. Now, the servos are all slightly different. For each servo, you need to check what pulse length corresponds to what angle, but 1 to 2 milliseconds is common. So in this example, let's see, I've got two versions here. So in both cases, I'm spinning it. This is so common that here I'm using an Arduino servo library that is a library that makes the pulse width modulation. But all you need to do is set up the registers. So here, rather than using the Arduino library, I'm talking directly to the registers using what I showed you from the data sheet to do the pulse width modulation. Same sort of thing. This is doing the pulse width modulation in the SAMD processor. It's a little bit more complex to set up the registers, but that's an example of that. So you use servos not to spin things, but to orient things. So a control flap on an airplane or a indicator for a speedometer on a dial. You use things where you need to control the angle, or a robot joint. BLDCs are brushless motors. And there are many, many, many different kinds of these. There are flat ones. There are ones that are designed, for example, to run fans. There are one in-runner versus outrunner is which is fixed and which rotates. But this is what they look like. So in a DC motor, there's magnets and coils. And as the motor revolves, you have to keep flipping the direction of the current in the coil. In a simple DC motor, like I showed you before, that's done mechanically with brushes. A BLDC doesn't have brushes. You do it electrically. And the benefit of that is it's much quieter and it's much more efficient. So a BLDC is wired as 3 coils. And then what we do here is we make what's called a half bridge. So this goes to ground, that goes to the supply, ground, this goes to the supply and ground. So each of these half bridges can either be a source or sink of current. And so what you do is you first pull current from there to there, then you pull it from here to here, then you pull it from there to there, and that makes the current go one way. Or we can pull current from there to there, there to there, there to there, and that makes it go the other way. And so by controlling that switching, you control the direction and the speed of the motor. You can get chips specifically to do that. And these, this one goes up to, say, 1 amp. And then beyond that, you get what are called ESCs, electronic speed controllers. And so these are modules that have the triple half bridge built into it. And so you provide the pulse width modulation signal, and the PWM signal is just the same as what we're using for the servo. But now it can do much more current. So for these BLDC controllers, the cost and the current roughly are the same. So it costs about $1 to do 1 amp, $10 for 10 amps, $100 for 100 amps, $1,000 for 1,000 amps. 1 amp is like a little model car. 10 amps is a small drone. 100 amps is a skateboard. And 1,000 amps is getting into the range of a car. And so for a few amps, you can make the circuit yourself. Beyond that, I would just buy one of these ESCs, electronic speed controllers. Simple ones are feed forward. You just step them, but you're not sure if the motor is following you. More advanced ones are adaptive, where as you switch the transistors on and off, at the same time, you can measure the current flowing, and you get a signal that tells you how the motor is turning. And so closed loop control is, you don't just hope the motor keeps up, but you can actually, the motor follows the signal that you're setting. So in-runner versus outrunner BLDC, that's a choice where if you make the moving mass on the outside, you can reduce the maximum, the RPM for maximum efficiency to say on the order of a kilohertz. And that's widely used, for example, in drone motors to not need gearing for them. So BLDCs are quiet and efficient motors, and are very quickly replacing brushed DC motors for all of their benefits, because it's not very hard to drive them. now we get to maybe the most important thing this week, which is stepper motors. So here's a motor, and I'm varying the direction and the speed. And then here you'll see, I can spin it continuously, but I'm also doing very fine motion. And I'm varying how far I move it. So what's in a stepper motor is let's see, not wiring, I want winding. In the stepper motor is there's a rotor that rotates that has permanent magnets. The stator has coils wound, and then there's teeth going between them. And so what's going on here is electrically, the stepper just looks like two sets of coils. So driving it is two sets of coils, and the motor rotates. But the way they're wound is there's one coil like this. And then these are connected alternating. So there's two interdigitated sets of coils. And these are oriented so the magnetic field they generate goes this way. And depending on the direction of current through the coil, it can either point in or out. Then in here, in the rotor, I've got permanent magnets, and the permanent magnets can point in or out. And then these are chosen so that the ratio of the number of magnets to the number of coils doesn't divide, so they slightly overlap. So for any one setting of the current, there's a direction where the magnets are happy. Then if I move the current to the next set of coils, the magnets aren't happy where they were, they want to align with it. And so by continually toggling between the steps in the current, I can pull the magnet successively to each coil. And so the angle of a step is the step between these teeth, and 1.8 degrees is typical for that. And so what that means is rather than just spinning freely, I'm putting in steps, and the step is moving the motor a known angle. And so you don't use a stepper where you just want to spin freely. You use a stepper where you want to be able to turn continuously, but you want to know exactly the angle. And so these are used almost uniformly in, for example, the machines that we're making. So when you make a machine and you move an axis, we use the stepper to move it. Now, this is a chip to drive steppers. This is out. Oh, wow. This was out of stock. This seems to say it's back in stock. That's exciting. This was out of stock through the pandemic. If that's in stock, I'll order a bunch of them. And I would encourage you to do that. This is a wonderful chip. So there's a lot going on here. From the outside, this goes to our stepper coils. And then there's really just, on one side, we put in the voltage, and the voltage to the motor is typically much higher than the voltage to the processor. And then there's just two pins here going in step and direction. Step says, I want you to make a step, and direction says which way to turn. Now, inside the chip is much more than that. Let's see if it has a, yeah. So there's a ton going on in here. These are the two H bridges driving our stepper. There's the charge pumps to generate the high voltage. There's the sensor for overcurrent. And then in here, there's waveform generation and microstepping. So one of the things this knows how to do is, rather than just slamming the coils on and off, it knows how to shape the current pulse going through it. And then the other big thing this chip knows how to do is what's called microstepping. And so to understand that, if we look at the two phases in time, we can have one coil be on, then the next coil be on, then we could have this coil be negative, then that coil be negative, where we're just turning them on and off. And each time we make that transition, if you look at the coil winding, the stepper goes from being pointed to that coil to that coil. But what we can do is micro stepping is where in steps we reduce this current, and in steps we raise that current. And so it means the stepper can make steps smaller than the coil winding. And so that's called micro stepping. And this chip knows how to micro step down to 1/256. Now, the micro steps aren't as accurate as the macro steps, but what using them does is it's much smoother. Rather than going chunk, chunk, chunk to each coil, microstepping lets you very smoothly move between them. And so in the code here, what I'm doing is the main loop, let's see, blinking here is just blinking the LED. But what I'm doing here is I'm varying the microstepping. And so on the schematic for the circuit, this is that chip. And I've got pins controlling the microstepping, and then it goes to the stepper. And I've got another pin that is controlling the total current from the motor. So that's driving the stepper with a stepper chip. Alternatively, here I'm driving a stepper, and it's doing the same thing of varying the angle and direction. But here I'm doing it just with an H bridge. So I've got two H bridges, and each H bridge has its extra current. And then in this case, in the software, now what I'm doing is one of these is a stepping sequence. I'm doing the stepping in software, and then I'm going through the cycling of that. And so instead of using the dedicated chip, in this chip, there's a ton of logic built into it to figure out how to make the stepping. If we go back to that system diagram. Yeah, there's a lot of logic in here for the chip to figure out how to do the stepping. In this example, I'm doing it all in software. So in software, I'm figuring out how to make the stepping. And so this doesn't depend on a particular motor control chip. It just is an H bridge, and those are pretty generic. And then in software, I can figure out how to control it. And so we've gone back and forth between using these dedicated chips and just doing software stepping. Yeah, Stephen is noting micro stepping is reducing torque compared to having just the current full on the magnet. Okay, so that's driving stepper motors, which we use when you want to do continuous positioning. And there are a number of vendors that make these. One night, Trinamic has come out with really nice motor control chips that are possible. And these work very hard. Oh, they were bought by Analog Devices. That's very recent. Analog Devices is a local chip company who I like, and so they bought Trinamic. So these make motor controlled chips that optimize the stepping waveform to make smooth, quiet stepping. And just like the BLDC, open loop stepping is you just make the step and hope it does it. You can sense the current coming back from the motor, and closed loop stepping is to confirm that the stepping happened. Okay, a few more final quick ones. For AC loads, what's called a hockey puck is, this is a logic input on one side, and then it's opto-isolated, which means on the logic side, there's an LED actually making light, and the light goes to the AC side. And so there's no electrical connection between the AC side and the logic side. And then on the output, it has a solid state relay. And so that's the easiest way to switch AC loads. And the one note to be aware of is the color of wires varies in different parts of the world, annoyingly. But you want to switch the hot side. So AC comes from the power company with one side that's not quite ground, but near ground, and then one side that oscillates around it. And so you want to switch the high side coming from the power company so that the appliance isn't energized. And then there's the low side and ground. And so your microcontroller comes to here, it gets opto-isolated into here, and then that switches the AC load. And these handle just about any voltage and current. These are very versatile. And so, yeah, the colors are different in different parts of the world, but that's how we handle AC loads. Shape memory alloys, I don't recommend because of the success of artificial muscles. So artificial muscles, this is a science paper on fishing line and sewing thread. And let's see, we've had a number of different examples of, this was a student doing an example where this is an actuator that's a tendon that pulls on that. And that's made by, he talks down below of, you take conducting thread and you wind it into a coil, and then you double wind it. And then by putting a current through it, you vary the heat that varies the extension. And so that's a good way to make things that act like muscles, artificial muscles. I had shown this for another annoying ad. I showed this in a student review, but I'll mention it again. This is former students making actuators where you vary air pressure in bladders and lets you make these flexible, soft robots. And let's see. This was a former how to make student who made this nice module designed for programming pneumatics for soft actuators. And with that, we're up to, let's see, Chris is telling me about uBlock to block YouTube ads. The reason I don't have those installed is it's an arms race, and they keep, there's always an arms race between what blocker works and then what you need to block it. So I've given up on that arms race. But what I want you to do is pick any output device and measure the power. So to do that, you need voltage and current. Oh, Hank says it works. So, okay, I should add that. So I'll make a note, uBlock. So measure an output device. Okay, Chris says it's been working stably, so I'll investigate. And then I've described LEDs, array of LEDs, displays, OLED, TFT, power transistors, speakers, DC motors, servos, BLDC steppers, AC loads, and then some other kinds of actuators, and pick an output and make it do something. And again, the example I gave is Ling Dong, who actually did everything. He went crazy this week. Keep an eye on your final project. Time will run out. So ideally align it with it, but pick an output device for the week. And then all of this is background. Machine building is going to be all about the motor control at the heart of the machine building. Final questions, comments? If not, Monday's going to be a great recitation. We're going to be updating this page. You're going to be hearing from a number of the star machine builders in the network on machines you can make. And then next week, we'll start the group machine building assignment. And as always, the three, let's see, is it still 3 amigos, or do we have gender balance on Saturday? I don't want to make Saturday morning gendered. So the gurus for Saturday morning are available for coaching on output devices, and then see you Monday for the machine building recitation.
Neil.
Yep.
I just found out about that you have been nominated or elected as the National Academy of Engineering in US. Congratulations.
Okay. Let's see. Thank you. Yeah, that was a nice honor. There's a National Academy of Engineers, and it's a nice honor to be elected to it. So thank you. Okay, so with that, happy output devices, and I'll see you for the recitation Monday. And thank you, Benno, for noting that. Okay, bye-bye.
Bye-bye.
Adiós, adiós.
Bye. Hasta luego.
Chao, chao.
Hasta luego.
Nos vemos.
Hello.